Okay, find that. No, a lecture record. Almost halfway through the course now. These are mine. Lab. We build trees to help us to this, how we visualize, the different paths. Get it wrong is to have a change by a little bit to get to what we were talking about on Tuesday about us having to be very sharp and very, very for assessments. It's all about how we probabilities, how we estimate. We got to be prepared to we use. In your management, with our results, then they sit on the other, they see to show that we're pointing at them. It's fairly clear by the acreage, it should seismic, right? And some have gone on senior managers, and when we start realizing changing one of the percentages there from 50% to what, 40, 45, 46%. Around a totally path. So, yeah, you listen to us. The time going to drill some to me, and I drill. It's because I've been there before. And these things are built. Interrogate people, and if I find 50 probability is because someone was out last night with something in the morning, I say, yeah, no, 50-50. Going to be very good. Okay? So either the estimation exercises that how the mark, to use a bit, lookalikes are a good one, get the experience from somewhere is another good one, interview people in expert. We're not going to ever get it right, so we just got to have a wide to make sure that our results are within. That's the way to take home from what we've done. There's no science here. There's nothing that can be said is right or is wrong. It's all whatever, the flavor of the consumer and the client is. But we've got to be professional when we do it, and the managers will have some expectations when they receive it. So as long as we are clear on that, that's fine. Now, way from having to estimate things. It is this. We all understand what it's. Many are enough. Our money we want not occurring. The actual question: more than X, say, or more than else, right? Or what is the probability of getting a negative MPV, right? That I want to know. I don't just want to know that this case, exit, I want to know what's the chance of taking the path. Look comes in. Okay, so any idea by anyone in the class about in something working, and I describe it if you say anyone had Monte Carlo is or does. I've got no idea of what Monte Carlo is or does. 32 students. Do we or don't we? I think we do, and I think we don't, right? So rather than start hitting you with theory, should we do an example instead? Okay, we will do a mechanical example. You know, a mechanical device has got a couple of pins that goes through. So all of you mechanical engineers, maybe start thinking of something, you know, and maybe attach money measures to the end of it. You know, what if, you know, there's a loss? What if there's a gain? So the same way others, you know, the electrical engineers and chemical engineers could be thinking about examples that apply to their professions. Right, so the example we had, and we will switch from this to the old computer here in a moment. Maybe we can do it live, okay? The example we had is, I think this is all about the example we had. Good, so I don't have to switch much, but I will when we have to do the actual model. So you had a chance to look at this? No, I didn't put this like yesterday or the day before, but I mean at least a couple of hours before the lecture. Maybe some of you did have a chance to have a look at it. Nothing simpler than, and I picked this from the internet. There's the website there, you know, vertex42.com. I mean, it's just an example. So we've got that little pin thing there, you know, to build. It's got like a housing there. And there's two, if you want, washers on each side of the pin, and the central part, you know, the one that's probably going to go moving like this, it's the middle one there, is the C part. So we've just got a machine that stamps each one of the, say, 4 parts, if you want, in line. So it's not, we don't have 4 different machines doing this and then we mix it. It's much simpler than that and much more artificial than that. You know, one machine does the 4 pieces, generates each one of the 4 pieces and tries to assemble them at the end. And if fails, the whole 4 pieces go to the rubbish. If it's properly assembled, the piece gets accepted. Okay? So we had a look at the piece there, and we are using Monte Carlo in establishing the manufacturing rate of rejection or acceptance for this device. We know that some machines, no matter how good or modern they are, they could still have an amount of tolerance. You know, they could still have an amount of variability on the pieces that they produce. This is more like 30 years ago when I was in mechanical engineering. Nowadays, the tolerance is much smaller. You know, the machines are much better. You know, many less pieces, I am led to believe, get rejected. Okay? So let's assume that this is a 35 years ago machine that actually has some you know, space for failure there, for imprecision. Okay? So what we do know is that the distance of the housing, you know, the D, like space there, is somewhere around the 33.5 centimeters. Okay? But it could be a little bit more than that, or could be a little less than that. If it's a bit more than that, it will allow things to fit nicely, to move. But if it's too much more, it could make things a little sloppy inside, and we don't want that either, right? If the housing comes up a little narrower, it's not going to allow the pieces to fit in, right? Although we could get lucky that for that pass, when the housing got narrow, the machine also created the pieces A, B, and C a little bit narrower as well, and they fit. So that piece would go through, right? I don't know if that's how mechanical engineering works, and in jobs for end machines today, I don't exactly know if the way it would appear, but if it's lucky enough and all three parts fail on the narrow side, even if the casing fails on the narrow side, the piece could still be assembled perhaps, right? In many cases it won't. So each one of the two, if you want washers, you know, A and B, they measure 3 centimeters, okay? And the distance there, the width of the C, of the part C there is 27 centimeters. So we seem to have a problem that makes sense. We got one part that measures 27 centimeters, 2 parts that measure 3 centimeters each. So when the 3 put together, we should be around the 33 centimeter mark. And we got a little bit of leeway there to install it in that housing there, which is meant to be about 33.5. But does that happen all the time? Well, we think the hinge appears to be properly designed as parts A and B and C will fit in the hinge housing clearance nicely and the assemble will work properly, okay? So, but here comes variability. Now, here comes reliability of the process of the parts produced. Reality shows that not every mechanical part can be produced at the exact measure. Tolerance must be considered, right? We know, start representing this as equations now, because we're going to put this in an Excel spreadsheet. So we've got to come up with simple equations like this. So we know that if A plus B plus C is greater or equal than D for any particular linear run of the machine that has produced the 4 parts, the hinge has to be rejected. Why has it to be rejected if it's equal D, if A plus B plus C are equal D? Because the hinge will fit, but it'll be too tight, right? So we need it to move, and for that we probably need a 0.000, like space or something, or difference. So we are saying if it's too tight, we don't want it either, right? That is the reason for the equal being there. If, again, from the practical point of view, the company considers that if A plus B plus C are equal D, that hinge is okay, then you would have to remove the equal sign from your equation. Why could that be okay? Because the company now it's going to be tight, but as soon as we test it, it loosens up a little bit and it's fine, right? So kind of quality control will fix that tightness. I don't know, again, if that's how mechanical engineering works. Are described by triangular distributions. If all of us, as I mildly hinted, have had a look at the probability refresher by Murtha, the one I gave to you last Saturday, and I was hoping it's being looked at by today, probability is nothing more than the histogram that represents how your data is grouped. From the probability of Monte Carlo, from the point of view of Monte Carlo, the distributions are our source of data. That's what our data is for our problem. That's where the value for A comes. That's where the value for B comes. And that's the value for C and D will come from those histograms that we are feeding the model with. We are telling, pick your data from here and pick it in this way. Triangularly distributed, evenly, triangularly distributed, loaded to the left, triangular distributed, loaded to the right, whatever, right? We describe it. Log normal, uniform, like it could, the piece could come at any value within this range, all equally likely, all equally probable. Normal, it could be hyperbolic, it could be whatever, right? But we have to know what we're putting in. That is the issue, and we have to be able to defend what we're putting in. We have to have history, we have to have expert opinion, we have to have all the material that allows us to keep our jobs, you know, when we are asked. So A and B, the washers, are going to usually come out at 3 centimeters, but they could be as small as 295 or as high as 305. C could be anywhere from 26.8 to 27.2, right? Uniformly. So that behaves, every point within that range is equally likely, all right? The housing, again, is another uniform distribution, so it's a pretty boring problem. Could be anywhere between 33 and 34, right? So there's a number of occurrences of the housing there that it may come up with 33.5 or less. Could even be 50%. We don't know. But maybe the combination of all of the others may allow a number of those pieces to go through anyway, because it just happened that the other pieces got made small as well. And lucky, they fit. Pretty unrealistic problem overall. For educational purposes, you know, we are going to be happy with that. So really what we're going to do, you know, we are going to have the equation. We're going to say A and B are distributed triangularly as per our definition. C and D are going to be uniform within the ranges that we have divided. Then we will combine all this, you know, the juice blender. We'll throw on all of that onto an Excel spreadsheet that's connected to at risk, and it will run it for 10,000 or 100,000 or 500,000 times if we want, and it'll come up with the rates of failure. But we've got to define that answer. What do we want in the answer? The percentage of times that it fit, or perhaps just an on and off type of result in which this many times it made it and this many times it didn't make it. It didn't make it, or some other way of seeing it. We've got to define what's the best for us for the business case that we're trying to make, right? The calculation is still the same, but we may want to have a cell there that shows exactly how we want to see the result, okay? So we got that. Let's not talk about that yet because those are the results. So let's, for a moment, move to the model itself, and we can build it. Yeah, so it'll give us an idea of how to operate with at risk, with my old ancient version of it, which is 5.0, and you will have the chance to use 7.5. So there's a quantum leap there between the two versions, I think. What I saw yesterday on Precision Tree, they were not too different. I mean, so maybe they have some enhancements, but it didn't look like the software I have is out of bounds in any way. So let me see if I can do it. What happened yesterday to 2 students? Yes, you. What happened? Work. Why did that happen? The same thing happens with that risk. Or, I mean, it's not doing. Remember what? You don't know, you don't. We worked it out. The same thing will happen for at risk. At risk by that, right? And you have your model. Tree icon or an Excel spreadsheet. So if you save it and then tree, you know, or you exit and then want to come back, there's my model. You know, you see your Excel thing, click twice on it. With Excel only, you have to recall it from Precision Tree or from at risk, which is the tool you use to build it. Excel doesn't know it. So Precision tree, which knows it. At risk, which is identify and be able to work with it too. Okay? So that's just a simple learning today. A few other problems did well, that could render inadequate a little bit, so we had to go back. For not incurring those minor issues. All right? Okay, so I need to hopefully hook up the ancient beast. Don't feel bad about it or anything. This is just part of I know a little bit of sharing there with all of us, as to be aware of what can happen. Okay? There, does it do it? Does it do it? Does it do it? Does it do it? Or do I have to do something here? Come on. You can do it. What did I do the other day that it worked? Such good fun. Why isn't it doing it at all? Why is it not doing it? Why is it not doing it? I haven't pressed that. Better. But now I can't see it here. How do I get it back? How do I get it back? There. And I can't see it there now. What have I done? Ugh. It's not there yet. It's not there yet. Why is it not there? Why is it not there? If I do that. Do I have any expert here on ancient equipment? No, not really? Okay, I got it hooked on VGA, but that's not what I got on my screen here. Disconnect projector, duplicate, okay. Yes. Okay. There had to be one expert here on ancient equipment, and that obviously had to be me. Okay, let's see what we can do here. I've got the model, right? This is not at risk, so I'm gonna get out of it. Otherwise, I will call the model and it will not identify it. All right? We're still seeing it? Yes, we're still seeing it. See, I got risk 5.0 and precision tree 5.5. You had the luxury of working with much more advanced versions. Okay? So that's my at risk. Right? You can see it there. Right? It's over there. Once we got that, we got our Excel working with that risk. Yesterday we had our Excel working with precision tree, had a different pull-down menu, and so on. Okay? So I'm going to call the model. I think I have it. That's it. We got it, right? So it's nothing more than a simple equation what we have here. But first, we've done what the text of the problem told us. Now we've introduced the distributions for each one of the parts. So let us click on part A. See what comes up on the what is it called? On the formula, thing. There says equals risk triangular 2.95,3, right? That's what we ask it to do, right? Say it's going to be 3 the most likely. The lowest is going to be 5, and the highest, and the lowest 3.05 as well. So it's not that difficult. It's basically I'm just going to go to another cell, which I'm going to put a number there, 4 or whatever. Right? I don't even need to do that, but I can go to at risk, okay, to define the distribution, and it's asking me, what do you want, Carlos? And I say to it, well, I want a triangular, okay. Yep. And I think it was expecting me to put the data there already. All right, so let me double click now. I'm sorry, a little bit rusty here. There we go. You see? So we can basically just go to the formula here and start sticking the number we want. It's given us something. It's definitely taken the 4 as the middle number, but the 4 there, yeah, as the middle number, but it's saying it could be as low as 3.6 and as high as 4.4, right? We could change that. We could, let me type there, and I'm going to make it skewed. I'm going to leave the 3.6 on the left-hand side, but I'm going to put 6 on the right-hand side. It represents it to me already. It's showing me what I've got in there. I'm saying to it, it's 4, the 6 is on the low side, 6 is on the high side, so it understands what I am saying to it, right? That's all you do. That's how you define your cells. You go to your A cell, to your B cell, C cell, and input exactly, what the problem is asking you to do. Okay? So look, we're going to leave that for now. It's that easy. I'm just going to close this. I don't know if it kept it or not. No, I didn't, because I didn't say okay. But there are other distributions that will ask you for other kinds of data, and this has got to do with the probabilistic backing of each one of these things. If we want to define a distribution of a different type, like a log norm, for instance, it will ask you different things. It will ask you, the data there means different things. We're not going to use log norm variations, but you've got to put deviations, and you've got to put a few or other statistical metrics that define distributions. Okay? We're going to go the simple way on most of what we're going to do. I never wanted to make this a probabilistics course. We would be bored to death, and we would be here forever. Yeah? All right, so that's what we got. So I've done it. I've done, the 2.95,3,305 for part A, because that's what we defined. I've done it, I have repeated for the triangular, 2.95, 3.3, and 3.05. Part C, it told us it could be anywhere from 26.8 to 27.2. That only required 2 numbers. We didn't have to put a middle one. Why? Because it's a uniform. All you need to know is what's the lowest possible and what's the maximum possible. It only requires 2 numbers to be defined. Yeah? Part D, same sort of thing, uniform, and it says it's there. On the formula it says risk uniform, risk uniform. The other 2 say risk triangle, risk triangle. Okay? That's it. That's how complex our simulation is going to be. Those 4 lines. So first, we got the model there, right? I have also defined it as an output. I want, after I've done the 100,000 or the 500,000 runs, I want the package to show me what the results are, so I'm able to play with them, start interrogating, the resulting distributions. So what is this distribution calculating? D5 plus D6 plus D7. Yep. So it's calculating the sum of A plus B plus C. Yeah? We don't want that to be ever any larger than 33.5, because that's the maximum that the casing is going to ever have. But in absence of what the casing measure is for each one of these 100,000 pieces that we're going to build, we don't know whether the casing is going to be, the assembly is going to be accepted or not, right? But at least we got a view of how often this could be under 33.5, or under 33.3, or under, 32.83, or whatever. We can interrogate and we can start looking for percentages. Not a very useful answer at the moment, because we still don't know whether the assembly will work with this data, right? What we got on the other one? On the other, we've looked at the information differently there. What have we got there? All right, we got if D8 minus D7 minus D6 and minus D5 is greater than 0, then it's a 1. If it's not greater than 0, then it's a 2. What I'm looking here is for how many pieces, blunt number, how many pieces get rejected and how many get accepted, or vice versa, depending on, that's what that formula is telling me. And the last formula down there is D8 minus D7 minus D6 minus D5. That is the more complete one that will give me the most information, because that will take the measure of each one of the 4 parts, sweep, 100,000 times sample A, sample B, sample C, sample D, determine if it's going to be able to assemble the hinge or not, and discards it or lets it go. That's the next one. Sample A, sample B, sample C, sample D. Can I build it? Yes, done it, and so on. That is the one, the only one out of the 3 that I've shown you there, that is more or less going to show you the most useful type of information, of answer. But we can have all the answers at the same time if we want. If we had larger models of sequential, assemblies, a whole car or something, we could have it in at risk. We could interrogate, how many times the alternators got assembled correctly, how many times, a carriage, got done properly. I wouldn't even imagine the formulas there because I don't know, but you could have a sequential piece of equipment in which you build, in which you can interrogate your model at any point of your interest. So that's it. That's a simulation model. Oh, yeah. Well, it doesn't look more like 4 cells to me and something that combines them. How do we make this click? How do we make this run? How do we calculate this 100,000 times? Well, we are in at risk. We can do that, and it's dead easy. All we have to do is go to, that's where we start the simulation. It will start running it, but this is where we do the iterations. Here I'm running 10,000 passes. How long do you think it'll take in running this result 10,000 times? Sorry? Half a second? Who said half a second? Plus or minus what? Plus or minus another half a second, maybe, but is that fast? Is that fast? So that one is something that I have prepared earlier, just like the cook shows on TV, it's one that I had prepared earlier. And I'll start the simulation now. Oh, more than half a second. Right.
It's ancient technology, though.
Yeah. The speed isn't there. I don't know what processor this is. It's probably not more than a Pentium. Does anyone remember the Pentiums? Okay. So we've got some reasonably mature people here as well. Okay, well, look, that's a result that we were looking for, right? We could start interrogating this. This is saying here, well, how many times, what are we saying? We like a positive answer, because this is measuring the space in the casing minus the sum of A, B, and C. So if the result of that equation is positive, meant that A, B, and C were able to fit into the casing. So we are looking for a positive answer here. What's the probability of a positive answer? What does it mean when we have a negative answer? To the left, it means that for that particular piece, A plus B plus C was larger than the size of the casing be assembled, right? So magically, I have the cursor there placed on 0, and this tells me the area under the curve that the piece didn't get assembled. So how often didn't it get assembled? Whopping 5% of the pieces got rejected. I'm sure the mechanical production planner would probably be in a bit of danger, if that, the probability of getting the pieces right. Could that change if we do 100,000 passes? Could it? I don't know. I only threw this in a little while ago. Let's stick another 0 in there, okay? How long will it take now? A few more half seconds, won't it? Okay, let's just do it. Sorry? Yeah, well, okay, there you go. The shape of the distribution is pretty sad, isn't it? Still doing it. As someone said, old technology. It's much faster these days. Anyway, it's done. But I got a different answer in front of you now. This is not the one we did before, the one with the negatives or the positives. So what is this one doing? What is this one doing? Just adding up 5, 6, and 7. Just A plus B plus C. So we know the distribution of of what was the measure of the 3 pieces put it together for any particular run. But that outcome is more or less useless to us, isn't it? Because we don't have the information in there of the spacing in the housing. So we don't know how many times that piece got assembled. Okay, so what do we know? What do we know that the measure cannot be? It cannot be more than 33.5 because it will not make it. When according to this, A plus B plus C are never more than 33.3. So it's not really what is driving the failure or the acceptance of the pieces. What is driving the acceptance of the pieces or the failure is the generation of the housing. The housing space is dictating whether it's going to be able to fit A plus B plus C there or not, right? So that was that one, and but we could have also done that one, and that was the 1 or 0, the switch on or off, where we could have the answer looked at differently. So do you realize how just by playing with Excel formulas, you can almost generate whatever you like to see your problem? Right? That is not a probabilistic distribution or anything. That was just a piece of logic that said, if meets the criteria, call it a 1. If doesn't, call it a 0 or a 2, whatever I put there in the formula. And then I just put a graph, or I didn't put a graph, but at risk, I was able to graph how many times one or the other result was there. So look, that's as much as I wanted to do there. So what should we do? Let's go back to the one that really gives us a good answer. Oh, did I lose it in any way? Let's just run it again, okay? I'll run it again. Halfway through. Something like this would have taken about a day to run in the 1970s, or something that would have been running. We did my first simulation of Monte Carlo. We had to basically code even the random number generating, subroutines, in Fortran or BASIC, and then put the computer. It was a little Commodore, 64K, university computer. The first ones after the big mainframes, and now we got a university computer. There were 2 available, and it was about 60 students, and we had to book time to use one of the 2 Commodores that we had. And then you put a simulation with 2,000 passes. You'll probably be there a couple of hours, waiting. So if your time had exhausted and your model was still running, you would have guys at the door, trying to break it down, and you would have locked the door and not letting them in because you have to finish your model. All right. Okay. So here we go. Now, this is so good. I say, this is so good, right? That's your result. That's your distribution. Now you can start interrogating. Right? You can say, what is the percentage of, of times in which the spacing between A plus B plus C and the hinge is more than 0.2 millimeters. Well, how do I know? I've got a big curve there. I mean, the area under the curve does it, is what it is. It's what your answer is. But, I mean, how do I know? I mean, I'll grab a ruler and start measuring it and make integration or whatever. No, it doesn't work that way. You can just do something very simple. You can just put the cursor there and start moving it. This is now a live answer. And you got your percentages, what's on the left of the point that you are interested on, and what's on the right of the point that you are interested on. So for some reason I was interested in how many times, what's the percentage of the times that the A plus B plus C is going to have at least 0.2, slack from within inside the hinge. Well, what's the area on the right-hand side? It's 74.9, which is that red piece, plus the 5% there at the end. So it's about 79.9. Or you can just read the percentage at the left, which is the one that doesn't meet the criteria of your interrogation. And it says 20.1% of the time it will not meet what I am trying to find out. Therefore, the complement of that, 79.9, it will meet the expectations of what I am interrogating it about. Okay? Simples? Really simple. In it? 2? I mean, need special training. You're going to get ambitious. I think it's going to happen with that risk. Right, for the basic things we need. But some of you, much more inquisitive, more things. Yeah? Funny, we were talking weeks ago. This thing's been progressing. When I bought the software, which is about 8 years ago would be, right? At several $1,000s, to my consulting gig. It had about 6 tools. It had precision tree. It was just that precision tree, and it had at risk, which was a separate tool like this in Excel. They had integrated it. Now they have at risk to at the end by some probabilities as a probability distribution. You can mix these with Monte Carlo. I think it's while putting probabilistic distribution on decision trees I love it. I love it. Some trees is that you got to go discrete, you know. And if you want to say that you need for a branch to change the we did yesterday with the. If you have a distribution there, that it will show you when the decision changes without having. What did we do yesterday? Type 49, 51, 48. Some of us would have started 49, 50.1, 49, 8, 50. No, it wasn't. Okay, so yeah, you do some large number in the middle, and that's not exciting. Now, good. So I hope I am enthusing you with this, because on a course like this, 10 half days, even less than half a day, I mean, what can we do? Well, what we can do is shower you with stuff and hope that you can start using it. Okay? Right. So this is what we're going to do on Monday, right? I'm going to prepare an exercise, just like the one we did for the trees. Yep. And right here, just like the one for the trees, we're going to prepare a little recipe for Monday. We will come to what room are we on Monday? G11. So that's the same one we started last Monday, yeah? On Monday of this week. So let's gather there again, you know, for 20 minutes or so, talk about the problem, and would you like to make that test 3? Have a number of questions at the end of it? Okay. The computer we're using that day, the computing room is 207, is the one, 207, so on this floor. One, it doesn't matter if we are together. Be good, huh? This one with someone else. Yeah? Did any of that happen yesterday? I want to know. Did anyone do it in Teams? No? Okay. Thank you, Silvanus. That makes me feel so much better. So much better. You wouldn't have a clue how much better that makes me feel. All right. Okay, so that little document that I uploaded just talks about what we've just discussed here, right? I mean, just a formula and more or less what we've done. I'll leave you to that, because we're already 1 hour into the session. I can't believe it. All right. What do we do now? Look, as I find the gaps and the holes, you know, we may next week just come back to complete a little bit of the thing, because we will need it for not value of information, but for real options. So, look, we'll do on Monday, just discuss briefly, but then we go back to trees again and a different subject. Okay, so that's it. That's what this course is. I'm trying to give you what we use out there. Okay, let's go to Monte Carlo. Someone said something? Sorry. Okay. Monte Carlo simulation. Okay. Okay, slideshow from the beginning. We'll try to finish a little bit earlier, you know, Friday, casual day, you know, and I've been casual all week, you will say. Thank you. Let's talk about Monte Carlo, but you more or less know what's happening, okay? Let's just go step by step then. We did that, so, you know, we were meant to review it, but it's, so what happened there? You know, we did a model, we did an Excel spreadsheet, an insultingly simple model with just 4 cells, but even that gave us enough to start to figure out what this is all about. You will have to come up with something, hopefully a few more cells in your models, in the ones that you're going to do for the assignment. On Monday or possibly Tuesday, we'll talk about the rules for the assignment, but it'll make more sense to you after we've gone through today and through the lab on Monday. Okay? So that's going to be an individual thing, right? So no teamwork on that one. Right? Area under the curve, just a small side subject that we may touch at the very end, and so on. Okay. So we want to talk about Monte Carlo simulation, and why are we going to do that? It's got some advantages, right? It basically, our manager is saying, great, I'm very happy to know that the base has got a positive NPV and that the high case has got even a larger NPV, but the low case has got a negative NPV. Thank you, that's telling me something. But how low is it low to start having negative NPVs? Those answers we don't. We put an analyst to the desk and we have it there for days running, you know, it is to the prices and everything to have a feel for things. That's not feasible. From the human point of view, the person would either die or go nuts, right? And we would have someone will sue us for mistreatment, or simply it wouldn't be cost efficient. I mean, the cost of generating the data that way just wouldn't make sense. So, comes in Monte Carlo, right? Not Monte Carlos, although someone has used that, but so what does it do? It allows the practitioner to describe risk and uncertainty for a variety of ranges. For our washers, or our pin, or for our casing in the previous exercise, as a range of possible values. No longer just a single value, okay? Rather than a discrete value. It is here where the company expertise equation for adding value. It's here what you did on Monday or Tuesday comes into the picture for adding value. The quality of what you do establishing those ranges is what's going to make the company add value or not. Okay? Monte Carlo can be applied to any calculation in any field of business. It's used for just about everything. Start looking around. Get into Palisade.com. It's got tens of small exercises of almost all walks of life. Could be an idea for there. Applies to any field of business, science, or other discipline. The logic is always the same. Simple spreadsheet, you know, define your inputs well, do the processing, define your outputs, and interrogate them, create the business case. With the help of computers, it can apply to very, very large problems. You know, I mean, air forces in the US, you know, big companies have some real big stuff going. But describing input distributions as known probability distributions would be handy. You know, if we know that we are making an assessment about fall on a certain part of Australia. We know that rainfall is distributed between this much drops and this much drops. That's a fact of nature. We don't really know, right? I mean, we would love to say we know what the distributions are that are going to govern our input variables. I am afraid we can't. So much I am afraid we can't that we do. When we do geological, where's the geologist of the class? There at the back. When it was a mistake by you, revealing yourself as a geologist. When we do geology, when we do prospect evaluation, you would say everyone joins their heads and come up with the distributions, log normals or log whatever. They're very scientific, right? You know what the sad reality is? Even the big companies, they do not go beyond triangulars. They don't know more. They don't know more. So even for geology, the triangulars are the most used distribution on prospect evaluation. PHPs, Woodsides. Anything else would be fooling ourselves, right? So they try to get it right from what's the lowest, what's the maximum, and where they most likely could be, right? If it's towards the left, towards the right. That they put a bit of effort in, but convincing people that they know what they're talking about is it's not that they don't know what they're talking about, but they can't be certain. Now, let me just finish this slide, and we'll talk about something else. So, in reality, that happens. We seldom know what the distribution is going to be. Some analysts have written that beyond triangular distributions, everything else is an absolute overkill. I mean, we are fooling ourselves, right? It's probably the most important single tool, Monte Carlo that is, to run a large number of sensitivities in one sitting. That's with more powerful computers than the one that you just had the chance to witness there. Okay. What's the next page? Okay. So risk analysis is really what takes us from sensitivity analysis done point by point to whole sets of answers that can be interrogated, and that are very useful to come up with the answers that we need. All right. A lot of this, or a lot of this, is due to this gentleman that I mentioned to you yesterday and the day before and so on, Paul Neuendorp. Now he came up with the book that I showed you, right? That it's not really a classic. But, I mean, again, no one is going to be disappointed if you buy it, because it's something that you're going to use the rest of your career. Decision Analysis for Petroleum Exploration. That's a young gentleman when he wrote it. That's a young gentleman that was totally silver hair and small and frail in the 1980s, when I had the pleasure of listening to him at the Kelvin Club with 150 engineers, sort of thing. It was brilliant. Now, is he still around? I don't know. I did a little search, and there's no information one way or the other whether he's still around or not. So, but he's to blame. What we did yesterday, he's to blame. The exercise we did yesterday, the decision tree we did yesterday, is a famous tree in the industry. It's the one that he came up with in this book, word for word, number for number. That the ball rolling, it's and what we're going to do today, a fair bit of it is chapter 8 of this book. I am going to have a good look, because it would be useful, whether we copy that chapter, asking admin, because I'm not going to do it, guys. See if we can provide it to you, right? It'd be interesting. Okay. Let's just keep going. Okay, definition of a probability distribution. It's important. Definition of probability distributions for random variables is the single most important area of a simulation exercise. It's what we spent all Monday and Tuesday almost doing and guessing, okay? Where possible, you should base the definition of distributions based on existing statistical data. You may be working with a phenomena that has been analyzed before, that has been measured before. Medical tests, there's been quite a few medical initiatives that have meant testing, patients, possible, whatever parameter of interest there is, and they have some data on some of these ones. Height and distribution of height of people in certain countries. Some are taller, some are shorter, and they are all probably normally distributed or triangularly distributed in some way. There is existing data for some things. Or if it's not similar or equivalent real type of situations, I mean, the good old lookalikes, something, near in fields, near in geology, elsewhere in the world. Then peer review or expert opinion. I mean, grab the advice you need. Sometimes it's going to cost. We're going to work out how much you could pay for, additional info, but it's a way of getting it. And if everything fails, use your subjective judgment or guess, stick your finger up there and see what happens, okay? In any event, make sure you test and fine-tune the distribution choices by thorough sensitivity analysis. If the person that did the tree yesterday had gone in, showed it to management without thorough sensitivity analysis, he or she could have been embarrassed by not perhaps having realized that part of that tree only required a 4% change from 50 to 46, to come up with a different answer. He or she should have done it. He or she should know. He or she should have had the answer for when the question was asked about how safe that person felt about it, and perhaps, what possible mitigation strategies could be implemented, to better that number. Okay. So known versus unknown variables. No, they can be sorted into those which values are known and those which are not known. It's a very deep thought that. At the time the simulation is performed. So for any given variable, if perfect information was available, the exact value would be known. We wouldn't need much. If we don't have perfect information, the next best approach is to use known control points and experience, something that is going to give us, a sense of that what we've assessed is more or less correct. But as our knowledge becomes poorer, the range may need to be expanded, meaning greater uncertainty. Okay? But if we are totally in the dark, a single estimated average could be used, or a triangular distribution, or even a uniform one. Right? So back to sampling. I may have talked about sampling on a different sort of presentation that I was doing, so that was still here. We haven't spoken about sampling yet. I said here that it has been stated before that the sampling process is the heart of the Monte Carlo simulation. Probability distributions are converted to cumulative probability distribution plots. This you know well because you have gone through the probability refresher, MRTA, so you know exactly what I am talking about. Monte Carlo software converts input probability distributions into cumulative plots, which is what it will use for sampling. Where the distribution does not easily fit known distributions, the cumulative plot is built by calculating the area under the curve in a graphical manner. MRTA did it, grabbed a curve that it was funny looking, and he divided it in different, segments. It's the way of doing it. You do, which is also called in, in operations research and linear program, it's linearizing by segments. Okay. Why do you have to linearize? You can't use curves. If you want to represent the exact equation of a curve, you've got to go into integration, right? And we're not going to go into integration for these things. We've got to get like simpler techniques and results. So if you've got a curve like this that you want to represent, well, you break it in small pieces where you can represent the curve in small linear segments that more or less follow the shape of the curve. That's linearizing by segments. Avoids having to use integration or derivatives or whatever deeper, because we are not going to achieve it. Okay? So, where the distribution does not even fit non-distributions, the cumulative plot is segmented. Okay? It's highlighted that the practitioner does not need to select a known distribution for a variable as long as it can be drawn. If you guys don't know what a variable, what the distribution is that could be used for something, but you have the data sample, well, You build the histogram yourself. You build the cumulative plot yourself. And as long as you have that drawing, you can linearize by segments, you know, and create. There's a curve like that in at risk, and you can enter the segments, right? So there is a way. We don't always have to go with the defined things. How to build cumulative frequency plots. We enter the distribution. The software turns it into a cumulative plot because that's what it's going to need for sampling. Do we understand what sampling is? Can anyone volunteer an explanation of sampling? What is a sample? Sample is like taking a ball from a, you know, you think, or taking a. So what is sampling? Is at random going into a hole, into a universe of things and picking something object from that pile, picking a candy, picking whatever. So is what's on in Monte Carlo is a picking. All those distributions that we've entered is our data. It represents the data. The software will pick one of that distribution at random, right? It will sample. That is what sampling is all about, right? So what did it do in that step exercise we did about the hinge? We had A, B, C, and D. To produce one hinge 4 times. You went on to each one of the distributions, the one for A, randomly, stopped in a point, read the point in the cumulative, it built from the, right? This is what I'm going to apply for this. Then did C, then did B, or independently. None of them had anything to do with the result of the. They were independent. Important, because we are talking about dependency, and the world's going to come down, you know, we will think that we're going to hell, okay, when we start talking dependencies. But there's a lot of dependencies out there. So, sampling, picking a value from your distribution at random, totally at random. And again, repetitive. It's done by us inputting the distributions, by turning it into cumulatives and using it as a randomly sampling at the bottom. When the value gets established, goes bang, calculates the intersection with the curve of the cumulative plot, and that's the value for that pass. That's the value for passes, 1,000 passes made. Times for every one of the 4 variables we put in, it will sample 400,000 times. Okay? The problem with Monte Carlo is that we can't see it as clearly as decision trees. Decision trees is seeable. No, you can analyze it, you can print it, and you can see the map of things. Monte Carlo, it's a little bit more of a belief. Okay, so let's go through this. The table summarizes how to build cumulative frequency plots for various distribution shapes. Okay, normal. For normal shapes, the cumulative frequency plot will plot English now. The cumulative frequency plots as a straight line on a normal probability graph paper. You know those graphing papers and things, you know, with scales and funny thingies? Well, it will plot as a straight line on one of those, right? The log normal will plot as a straight line on log normal probability graph paper. Very smart. The uniform will plot as a straight line on normal paper. Just, you know, like not log normal or not anything funny or logarithmic. The triangular, the cumulative frequency is built by converting triangle data using equations given for left and right hand side of the mode. I'm going cross-eyed, but I mean, look, it's built, okay? Histogram is plotting the points for cumulative frequency and determined by accumulating the relative frequencies from minimum to maximum. Great, fantastic. Continuous cumulative frequency is built by separating the distribution into segments, calculating area per segment, and plotting as per histogram. I don't like any of the bottom three ones, but I like the top three ones a lot more. Okay, you all went through this. All right, you all went through this. So what was that? Mertha, or I don't think this is Mertha. I think this is this Neuendorf or Mertha? I could have made a mistake here. Just bear with me. No. Yes. This is Neuendorf. Okay. This came from Neuendorf. It's correctly acknowledged. Okay. So he's using here a given histogram. Someone measured this a net peak thickness of a find of a reservoir. We can see there that it's could be curved, right? Could be curvy like that, but it could easily almost be represented as a triangular, just by drawing a line on top. It could be any of the two. So what he's done, it's basically done the cumulative histogram for all those points, 1, 2, 3, 4, 5, and the curves come up like that, with linear segments, for each one of those. That's possibly good enough, for what we're looking for. Then, he's done it like, okay, each one of the 5 segments in the end is plotted cumulative to form a probability from right to left, okay? Those two curves are equivalent. They're just seen the other way around. Left of the curve or right-hand side of the curve, of the point that you're looking for. But when we got this one is when we were talking about, no, that's, if all we know is that the sample of points that we've taken looks like something like that, then we can linearize by segments, which is what we were talking about. We got Buckley's chance of coming up with the equation for that curve from a segment 100 to, say, 190, maybe. We are not going to achieve it. We wouldn't have to be a mathematician, to be able to represent that curve. So what do? We converted into what Neuendorf was doing before, where he had a curve by segments. We take all the segments that look like we could draw a neat a straight line through them, and we create these artificial segments, and we therefore replace the curve by a linearized curve, that represents roughly the shape that we are looking for, and we plot that one. The number of segments will depend on the number of neat segments that we define on the curve. For instance, those segments will depend on the drawing. Well, this bit here looks to me like it's pretty handy for a straight line. Yeah? From about there to there. It's, well, there's divide it in 2 then. Make that little bit there a straight line, and this little bit here another straight line. We'll have a perfect fit, or a better fit. 2. You didn't see my hand covering this bottom bit here, did you? Visually, to me, I can't fit it on a straight line for this segment here, because it's going that way. So what I would do, I say this bottom here, it's looking to me like I'm going to need a straight line there, that will be divided here in the middle, another straight line there, another straight line there. I wouldn't go beyond trying to blend the previous segments, because that would be bad. That wouldn't meet. So here, it's obviously the start of a new segment. How fat, how wide could that segment be? Well, I'd say about that. I say a straight line fits nicely there, so that would be another segment for you. Bang. There, here we got a curvy again, but that's nice. So maybe one from here to here, and another one from here to here. Then it turns again, one from here to here, 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 bang, bang, and here we may have a longer one there, a longer one here, turns here, 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 here. The way I would do it is visual. It's almost you run a pen, and those will be your segments. Therefore, you would turn a curve into no longer a curve, no longer a mathematical integration derivative series of Fourier problem or whatever it is, that needed to be applied, but on a very simple set of straight line, straight line, straight line, straight line, straight line, very easily plottable on a graph to build the cumulative probability that the software needs. Right? That's what the software does. Okay? So that's all I wanted to tell you there. That's what it's done there. Did I get it right with my segments? Whoa, this is ambitious. What did I say? There's too much of a gap. I would have done two there. I would have done to there, and here and here. So I don't agree with the book. Yep, he's wrong. Second, well, ambitious again. He went in just one line. Perhaps I was pedantic by wanting two. I wanted one here, so we agree on that. I don't like that. I'm fine with that. I'm fine with that. I'm not so fine with this. I would have cut it here. I'm not so fine with this. I would have do it. Maybe. Maybe. Okay. So what I'm saying here, what Neuendorf has done is what's going to be done. It's your baby. It's your interpretation. What do you feel comfortable with? It's your decision. Okay? So I didn't agree about 4 times in that graph. All right. That is the graph cumulatively of the segments he defined. He wrongly defined. Okay? That's a cumulative plot. Okay. So a triangular there. Those are the equations for those of you that are that way inclined, that you got to use to build triangular distributions. You got to interpolate, extrapolate, and doing a few things. Let me see. Okay, so building a cumulative curve. Now, insights. Practitioners will be more often than not be working with distributions created from statistical data. Hopefully, we will be able to hang our hat on something, that's out there. Hopefully, we won't have to build the curves. Hopefully, we won't get the cloud of points that we have to start plotting, right? So it'll be distributions that we more or less agree, that everyone knows and kind of agrees to disagree, and so on. The number of intervals or bins to be used on a histogram will depend on the data and the degree of accuracy required. Simplistic Paul Neuendorf did a number of segments. Specialists, highly pedantic Carlos wanted many more segments. I want it much more precise than Neuendorf wanted it, right? The consumer's choice. The method is not the maximum expression of mathematical excellence. I think you noticed that, yeah? Did you notice specifically, that it's not the actual, mathematical excellence, but it would probably irk most academics. Doesn't irk me. Why? Because I've been 25 to 30 years in the industry, and I know that some academy things fit very well in the industry, some have to be massaged a little bit to make it work. Okay? Despite the above, it gets the job done and allows a practitioner a method to work with probabilities. I need to make a decision about wells and things, and I can't call a mathematician or UWA maths department every time I need something. Without having to use integration techniques to find the area under the curve or something like that. We must not forget that we are not looking for the right answer. Where is the young lady that doesn't like me saying 85 is just like 90 or 70 is the same thing, right? We're not looking for the right answer from management point of view. We will not get it. We are trying to understand uncertainty and locate where we are standing in the picture of things. You know, chances of making it or chances of not making it, or 50-50. That's more or less what we are looking. Okay? So far the material reviewed is concerned mostly with independent data and distributions. That sounds like an ominous warning. Something is coming. Right? We will now explore the situation where there is dependency, conditionality between variables. Okay, let's stop there for one moment. I found in the last minute before leaving home, I said to some of you that I had found a table of statistical distributions, and I'm going to get out of this presentation because I'm just going to fire up something else, that apply to nature type of situations. I mean, what distributions can be used is almost what you could use to define your distributions for your assignment, right? So this is the competition to Palisade. This is the Oracle, where they produce Crystal Ball. Again, the competitor to our risk, and they got other tools that compete with Tree and that, okay? We will try to zoom this. How do I zoom this? Oh no, don't tell me I can't zoom it. Where? There. Bam, 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 bam. Very good. Oh, I could do that too. All right. Okay, so let me just see if this is a list that they have come up with. So how do I get to them? Oh, yeah, okay. Oh, this is interesting. How do I go to... Oh, yeah, I do. Okay, fantastic. I'm used to the touch screen now, and I'm getting a bit lost if I have to do this with the mouse. All right, so look, this is their contribution to what some nature elements could be represented by with distributions. So it says there, the normal distribution there, the mean value is the most likely, it's nicely centered. It's symmetrical about the mean, great. So you know that it's got the same area on the left and the same area on the right. It's more likely to be close to the mean than far away. That means the sampling, when the data gets sampled, most of the data picked is going to be from around the middle because it's weighted that way. There's more data around the middle. Yeah. The same thing with the triangle. So what this is applied to, it says here natural phenomena. Oh, thank you. That's clarified a lot. And it says there examples: people heights, reproduction rates, inflation. Well, there must have been studies around that have picked up, by Oracle, to be able to say those things. What about the triangular? It says the minimum and maximum are fixed. It has a most likely value in its range, which forms a triangle with a maximum. It stops short of saying it's symmetrical because it could be, shifted to the left or to the right, And there's no relationship between the left in the same area. Why am I interested in the area? Why do I talk about areas? Because area is the probability. The area under the curve is 100%. When you know what you want, and you can compute how much area is to the left of it and how much area is to the right of it, you know the probability. That's why you're interested in area. Would that be an exam question? Could be. No, I don't know. Come on. All right. So what does it apply to? When you know the minimum and the maximum, the most likely, useful with limited data. Is that why petroleum industry use it? We got limited data. Yeah. Sales estimates, number of cards sold in a week, inventory numbers, marketing costs. They might have their reasons to say that. Log normal, what does it mean? The upper limit is unlimited. The lower limit is 0. It's asymptotic. Yeah? On the right-hand side, it's more or less, it could go forever. But it's very unlikely to sample values from that forever part of the poorly represented. It's more or less all going to be from the areas that have some meaningful, visual here. So distribution is positively skewed. Funny, this is loaded to the left here, but they call that positively. That's the jargon. Okay? If it's inclined to the left, it's positively skewed. When it's inclined to the right, it's negatively skewed. So it's kind of the opposite. I mean, to me, I think the opposite, right? Situations where value are positive skewed but cannot be negative. Thank you very much. Real estate prices, stock prices, pay scales, oil reservoir size. Oil reservoir size, okay? A good probability of a good Monte Carlo model with natural variables and whatever, 4, 5, or 6 of them, they say it should come up with a log normal answer. Right? Should come up with a log normal answer. Should. Okay? Now, the uniform one, the minimum is fixed, maximum is fixed. And as I mentioned before, I use this for the hinge. All values in which are equal. When you know the range and you know that all values are possibly likely, are equally likely. Real estate appraisal, leak on a pipeline. We were talking with someone about pipeline work, thermal things. I don't know if this applies to hanging. Commonly used the card. This was 2 sides. So you can read yourselves there. There's a binomial there. There's a yes, no, which is more or less the one I generated. It's accepted and hinges. There's a beta. I never use 1. There's a beta PERT. I have never used 1. There's an exponential. I haven't used it for simulation. Right? And there's the other part of the card. I'm going to load this. I don't think I loaded this. I uploaded it onto the website, but I will. Okay, so you can, if you feel comfortable, you can use it as a guide for maybe some of your explanations that you're going to give to me. A gamma, similar-ish to the log normal in my books, a Weibull, a max extreme, a mean extreme. I think we're starting to here. A logistic one, which is almost like a log normal, but much more concentrated in the middle. Students. This is the surname of a person, student it was. So that's why it's got its name. Then there's Pareto, a Poisson, not Poisson, Poisson. Hypergeometric, negative binomial, geomatic, custom, defined by the user. What are these things used for? Well, that gamma 1 is demand for expected number of units sold during lead time. Okay, meteorological process, pollutant concentrations. The Weibull failure time in a reliability study, break of a material in a control test. This, used in specific industry analysis. What's that one? The logistic growth of a population as a function of time. Students. That I knew. Share them with you. See if you can. Perhaps use and some of that in your assessment for your Okay, so let's go back to Monte Carlo where we were. Shall we have a break now? Yes. 15 minutes? Because the next part is heavy. We're all going to be not very happy with it. Okay? Are we 6, 7, 13, 16, 20, 23, 26. This is a very good number, guys. I mean, we've been blessed with good attendances. There's a very small part of the course that is not here, which is great. All right, so we're going to do, after the next part, we will just wonder what hits. And so it's more hit you. It's something that takes a while, sometimes takes weeks, or sometimes takes all about, right? So let's see you with that because it's Friday. We are going to try to leave a bit earlier, yeah? Anyone post that? Or what's next? There's happy hour. Are you members of the UWA club? Is anyone a graduate? There's happy hour tonight, and there's a bit of music by the balcony and that, right? At the club, the UWA club. But you've got to be a member, I'm sorry. The funny thing is I am not staff of the university. To get a job with universities. Everyone knows me, that they recommended me to be a UWA club member. Though I don't really qualify. Been the club, it's just a letter of recommendation by, yes, Carlos. And it's a great club, I tell you. This is, we were nights. First Friday of the month is just now. That's business. So, do I become a W club? Several $1,000s on membership. However, UWA club is way more inviting, and it's good chance to do business. Some of the little bits pieces that I've done have been from dinners that I've had with people, and the way you've got to do it. It's a very, when you're all graduates from here, you will be eligible to become members. Think about it, $20 odd a month of membership. That's all it is. I'm going to speak to the general manager of the club now that I've been doing this plug for him, and maybe I'll get a free bottle of wine next time I go, or something. Okay, so let me talk about the assignment. People are starting to get nervous about it. Great, get nervous, get very nervous. People are starting to get scared about it. Not so great, don't get scared. It's simple, but it's got to have some base elements. There's got to be a calculation, yeah, like the Excel spreadsheet that we had there for the hinge. Hopefully a little bit more than that, maybe 2, 3. The important thing that it's got to have a metric. That calculation has to result that you are in cost, millions of performance, of reliability, volume. You want to less than. People that react well to whatever you're doing, there's got to be a metric. You are making something, a number. That number has to be dependent on the person as your input are A, B, and C, and D that we had in the hinge. Telling me where and how, and all the reasons why you used a certain distribution for. You use a triangular because that's what the industry found out, that variable behaves generally. If you don't know, then I use this distribution because I couldn't find anything, something similar on some other industry that works that way, so I've used it. I got no idea, I just used your Oracle there. I use that. Tell me why, to have some of your assumptions. So, have a little paragraph or two there about how you came up with your variables, your ranges, and the distributions. The model, hopefully, it'll be a little more intense than the hinge. 100 lines. But I mean, then you got to have, no, don't do 1,000 because it doesn't, it's not very 10,000. Try to do more. Try to smooth out. Also important, you need to have a view for what is good and what is not good. In net first, you want a net present value which is positive. So you compare your answer, your probabilistic answer, desire of yours. You want to have something that's more than 0. Then maybe interest because your manager has told you this project will not be at least $50 million NPV. Answer against that desirability on how long does it take to corrode? Less than 2 years, more than 2 years, or whatever it is, for instance. On ability, what's the minimum point? Anything less is not acceptable. So you test your answer against acceptable, right? Acceptable or desirable answers for your problem, and hopefully the probability wrong side of what you want is not so small. Say I want an NPV for more than $50 million. On my run, I only have 25% chances of anything wrong, but this thing is not going to get us a good probability of the $50 million or more. So here, and this is the smart part of it, what would you do with your input data? What would you change in your input data and do it, actually do it? So a higher probability of achieving the $50 million. I get a higher probability of achieving my 99.3 reliability. I've got a higher probability of my pipeline lasting more than 2 years. I've got a higher probability of curing 97% of the population or something. The simple answer is, just go back in my model and change the ranges. Yes, that is the answer. Does that give you any points? No. You're going to tell me why you would change. If you want more reliability, I just changed for X or Y variable, and I say, yep, that's giving you more reliability. Why? That change now use 13 chrome instead of whatever, lead materials or just wrought iron. Right? Or that change that I have in means that I have bought a new machine. Really can produce many more of the parts. Maybe, just maybe, you stick in the say a new machine is going to cost me $300,000, but I'm going to produce so many more pieces that I am going to not lose much money that I was losing before. You see? So your model doesn't have to be complex. I want the full expression involved in the calculation. Ranges and the distributions you used. I want your calculation. I want the graphs for all the outputs of the variables of interest. You click the outputs. of the cell where you are, and that will plot the result for you, and it'll be live. You will be able to play with it with a moving cursor and that. I then want that to test your final answer of your metrics against the desirable answers for acceptability. And hopefully your problem has to be done in a way that is 100% foolproof, right? Hopefully I want you to go back. I will buy a new machine. I will use different materials. I will acquire more information, drill a well. That acquiring requires, right? So there is a level of lack of understanding there. Maybe another well's got to be drilled. So that would have to be behind the of things. Yeah. Let's keep going with what we got today with the dependencies. Let's do the exercise on Monday, and hopefully by then the whole thing will be much clearer. Okay? Yes. I'm thinking so I can, do you want it marked before the exam? I think you will want to go to the exam with the result of that, wouldn't you? Say not necessarily. Not necessarily. No, you don't want the suffering, huh? Well, look, I mean, in my conversation with Zach, with the owner of this man, do you all know him? He's my one. With the 10 days, the assignments some 10 days before. So what does that mean? About the 8th. Right? I mean, everyone okay? I mean, this is a democracy. We can do. So, because sometimes I should demand. I am known to do whatever I like sometimes. Yep. So does that make sense? I need to understand that you got the gist. You know, you got to justify your inputs. You have a model that calculates. You have to test it against a desirable answer, and hopefully, your model doesn't meet the criteria fully, and you got to go back and redo something. That's what the assignment is about. Yeah. Okay. But I would have been marking on that weekend. Okay. No, it's okay. Monday? That's a Saturday, isn't it? Yeah. So Monday would be the 10th. Okay, Monday at what time? 6 a.m. in the morning. 5. We're negotiating here. Your negotiation skills.
11:59 p.m.
What if we do it 6 p.m. on that day? So, because I will need a hard copy of this, as well as an electronic copy per monk, you can put it in the box, and I can pick it up that night. I would pick up at about 7, you know. So if it's in the box by about 6. 5, 6. But I'm just thinking here, if I don't have the key, let's give us. If I can get myself the key for the box, then it's 6 p.m. because I can come and grab all the stuff and start that night. If the admin people will have to do it, and that's going to be 5 p.m. right? And then I don't get it until the following day anyway. So I need, let's just, okay, TBA, but around that time. Yeah, you got them another 2 days, man. I mean, they should applaud you. All right, good. Now for the fun. We did the hinge, and the 3 variables or 4 variables that we were sampling were all independent. Yeah? None of them depended on the result that had been sampled for the previous ones. They just responded only, they answered only to themselves. The size of the C part, you know, the moving part in the middle between the washers, didn't have absolutely anything to do, didn't depend at all on the sample for the washers. It's separate things. They were done on the same one after the other, sequential, but none of them took into consideration at all what had been sampled for the previous variable, what the result for the previous one had been. Unfortunately, that doesn't happen a lot. Most of the variables are dependent on, the variables are, their results will depend on the result of the previous one. And those of the results perhaps will govern the result of the next one, and so on. And that happens a lot. And that can all be distributed probabilistically. Okay? So what we're going to see now, and I have just spoken to John Power from admin about photocopying the chapter. There's not going to have any, the exam is not going to contain any calculations from this part because it's tough. Okay? But it may have conceptual sort of questions about, you know, and so on. But yes, he's quite happy to photocopy a whole chapter and something that we can give it to you, right? Or allow you to download on a USB. Okay, have we all fastened our seatbelts? Have we? Yeah. You're there? Okay, fine. Let's go for it. Variables, unfortunately, I would have added, may be related to each other. In fact, they often are, right? The sampling in our model must be performed in a way which replicates that dependency relationship, right? The one we did for the hinge didn't need to. We didn't need to consider what had happened before. Correlation analysis is one of the most efficient ways of establishing dependency between 2 variables, because how do we know that these things are dependent? You know, it's one of the problems. Again, practitioners may be well served by a quick and ready, a la Neuendorf. So what Neuendorf did is not anything that was unknown at the time. It's just that it was known by the pure sciences, statistical sciences and probabilistic and that sort of thing. It was known by mathematicians rather than simple oil people like we are. Right? He's a simple oil guy that translated this into something that we could use in the industry. Okay? So that's what his value is. Again, as I said, practitioners may be well served by a quick and ready graphical method for establishing dependency in order to avoid getting tangled in complex statistics. I remember a statistical inference that I did when I was at uni, and it was probably one of the subjects that I least enjoyed. So I am happy about this. A cross plot or a scatter diagram, even software like Excel, has scatter diagrams in which you can have a feel for clouds or points. You plot one variable against the other, and just the shape of the graph tells you whether there is relationship or not. So let's consider some situations as follows. That's, say, a scatter diagram that we plotted in Excel if you want, right? There's a variable A against a variable B, or a variable B against a variable A, whichever way you like. There seems to be a very much scattered cloud of points there. Intuitively, when I say dependency, would you think that that cloud of points shows dependency? No. It's very scattered. It's all over the place. There doesn't seem to be, right? For instance, if I sample a variable, a random value of my variable A, therefore, and I haven't even defined it yet, I could call it uniform, triangular, log normal, or whatever. I can define that that is my independent variable, right? It will be not dependent on what happens with B, but B will be dependent on what happens with A, right? So let's say I define my variable A, my washers in the hinge that we were doing, and it comes up with a certain value, say here, bang, here, just above the A here, right? Then we know that the next variable will take a value that is dependent on this value that has been sampled for the first one. It needs it. It needs the information of what's been sampled for the first value so it can define what happens with that second variable, with that variable. Here, I sample A. Well, it could be in about there, right? Okay, I sampled something about here for A. Well, could be between about here and here. And just for every point that you can sample in your random variable A, it's the same story, just about anything. There doesn't seem to be a tie between the values that variable B can take to what variable A can be. So that tells me that there's independence between the two variables without having to test it by chi-squares or chi-square tests and statistical inference. I mean, I can see it visually. There doesn't seem to be a dependency there, right? But what happens then for that one? If that is the observed cloud of points, and you get Excel to plot them for you, and it comes up with that plot between variable C and variable D, does it naturally tell you something different now? It does. It tells me that there is some relationship, that it will depend on what variable random C takes for what variable D is going to be. We know that if the value sampled for variable C is low there, variable D is going to be somewhere lowish as well, about here. Yeah? Not lower than that, not higher than that. You know that if random variable C is sampled here around the middle, you know that your D variable is going to be somewhere around there, more or less in the middle. The previous value that we were talking about will probably be as high as the next value that we are going to sample, which is towards the higher end of C. Yeah? So we go to C, the value that came up in at-risk sampling is high, bang. D then would be somewhere around there, on the higher echelon, right? Cannot be anything lower. So there is a relationship. Okay? We could simply have, I'm thinking here, I'm thinking aloud. I have obtained random variable C, recoverable reserves of my oil field by sampling, you know, I mean porosity, gross rock volume. I came up with recoverable reserves. And bang, what could my variable D be? I'm thinking aloud, maybe that's my net present value. Perfect. All I would have to define is more or less that curve, and we know it doesn't have to be curved, don't we? We don't want to get into integration. Difficult for defining curves. What would we do? We would linearize it. We may take one segment, two segments, three segments, four segments perhaps, That would be our NPV versus reserves value. We sample reserves, or the result of the simulation of reserves would come with the value, and then we do what? We're going to ping, interpolate on the linear equation that we have. All this is in Excel, not more than 5 cells, you know? And you suddenly have a probabilistic outcome for your net present value as well. So this is an at-risk thing, you know, running on, as I said, gross rock volume, porosity, you know, for factor, saturation, you know, recovery factor as well, and you end up with a number that is recoverable reserves. Then you just go bang and read into another equation that will interpolate into a straight line, and then you have a probability distribution for your net present value. How neat. Well, that's done all the time. You know what? You're going to do it on Monday. That's your exercise on Monday. We will do the gross rock volume, recoverable reserves, and we'll do as well. Okay? Now, the simplicity of something like that is that the NPV is justified by a line. Where did we get it from? Well, we had to model it. How did we model it? We model it discretely, right? So it'll probably be an NPV that is just low, medium, and high. It'll be 2 lines, because that's all we've done with the big NPV models that we have. All we were able to do is to calculate an NPV for the medium, an NPV for the high. So that's where we got that information. Pretty pedestrian, right? Pretty troglodyte type of work. We could have probabilistic NPV. We could have that, instead of being linked to just a simple straight line, we could have it linked to the NPV model itself on the reserves line, the production figure. All of the volumes that are generated by the sampling of variables, say 30 million barrels, we could go and tell the Excel economics model that it's got 30 million barrels. If the Excel economic model is smart enough, if it's not a dumb model, then we should have a calculated profile. We could have predefined it on a, let's give it 20% of that on production on plateau, and the other 80% on production on a decline basis. On an exponential decline basis. So, could be a smart model that reacts to the data that is entering, that doesn't even have to be calculated by the economist. The economist has built the model in such a way that it calculates, but the NPV doesn't have to be a straight line. It could be a volume going into a smart NPV model that regenerates the production profile itself, given what's received. Totally doable, and I've done it a few times. Yeah, I prefer that. Okay, so getting the gist, dependency. Have you seen this ad? The guy that offers, you know, you buy this set of knives, you pay whatever, and but I'll give you 2 sets. And then it says, when you think it's done, it says, but there is more. You know, I'll give you some. There is more. Let's just keep going. This is the simpler part of it. What about that one? What about that one? We can see, just like our previous slide with variables C and D, we can see that there is a dependency here. Can we? Yes? There is. The points are falling within a yeah? Below a certain line, they are not above. So, what does this mean? That it's not as easy as the previous one. It's not, we are going to sample C and we're going to read a value from D from a straight line. This is more or less, we are going to sample X. And sorry, there is variability as well on Y. It's not just going and read from a straight line. It's not just go and interpolate. There is variability on the next variable as well. So what this is saying, if I get a value, if I sample an x value roughly around here where the R is for the R for random, over here, yeah, which is a little bit left of the middle of the range available, then we need a value for the random variable y, bang, we enter the cloud of points. Not just a straight line anymore, not just a single thin line anymore. Now, that in itself's got a whole range, right? So what that means is that the sampling of the variable x, which is here, has defined the limits for that new variable to be sampled. Is what it has defined. You go from the R above here. When it crosses that line, then again, you're going to have to linearize that way, and the top one you're going to have to linearize that way, and this one probably you're going to have to linearize that way, and the same thing with here on the right. Well, when you intersect the bottom one, what you have found is the minimum for that new distribution that's going to be sampled. And you keep going up, you get the other intersection at the top, and you're going to find the maximum for that's going to be done. So all first sampling, you will have defined the low and the high points of the range for your next variable. And you would say, and how do I know what type of distribution that is? You see it from the graph. What that's saying to me, graph is saying to me, all those points are kind of equally likely. Any of them could happen. It's screaming a uniform. To me, it's screaming a uniform. There's no grouping within that area that suggests anything else. To me, you enter here, it's almost the same probability for those points. You enter here and here, the same probability for that lot, and so on. I don't see concentration towards the middle or so on. This is all Neuendorf's working and finding. So I would sample variable x, enter here, interpolate here, interpolate there, and I will get a uniform distribution for the interpolation of the next variable. That's the way that this works. What's created is an envelope of probabilities. I don't know, I may be crazy, but I think it's fascinating. I mean, no, once you get it, it's incredible. So that cloud of points seems to be like homogeneously, consistently distributed. There's no preference for those points. They are somewhere in there like a nice smooth cloud. But what happens with that? What happens with those clouds there? It's been simplified a little bit. Okay? We don't have curve things anymore, or well, we do. We don't have one here, but we've got curves there and we've got curves there. That's the one we were looking at. Yeah? We sample x. X would cut that. That would be the minimum for the next distribution. That would be the maximum for the next distribution, but I don't see any preference or grouping of the dots inside, points inside. That suggests to me a uniform. So that's what Neuendorf is telling us. Variable, it's going to be a uniform. Minimum and the maximum are going to depend on where that sampling happens, where the x happens. And it says the next one is a uniform. You plan that in your Excel. Those two cells linked. The first cell sampling the x variable is independent, it doesn't depend on anything. The second cell, you will define the minimum point for that one as what came up of the interpolation with the lower curve here, and you will define the maximum point of that one as what came up with the intersection of the upper curve and the points of the uniform distribution that you're using on your second cell have been defined by what happened on your previous cell. is a cascade. You know, the first cell happened, those results in the subsequent cell. How do you do that? I can't show it to you because I turned the computer off, but you remember the distribution there where I had a uniform and I said risk, uniform, brackets, a value, comma, another value, close brackets? That's the way it was defined, and I just had to type the two values in it. I typed them because I knew them, because the distribution was independent. But I now will not type those values. Instead of, on the left side of the comma, instead of type the cell where the intersection with this curve is happening, and it will record correctly the result from that. And then comma, the address of the other cell that's computing the intersection with the upper curve. So one feeds into the other one, is chained, is cascading. We will see that on Monday. We will do an example on Monday. So hard, Friday, drinking time, but on Monday, we'll all, you know, good and fresh, and we will see it better. The second one, same thing. The second cell will receive what's called in the first cell and will define itself. But that will be a uniform. That will be a triangular, right? So it'll be risk, triangle, brackets, space for the space for the number. Will require 3 bits of data. We can't type a number because it's not an independent one. We got to point each one of the 3 spots to the cells that are going to be generating that number from the previous sampling. Why do we know it's a triangular? Why do we suspect it's a triangular? You can see it. The grouping of the points. You can see it, right? They are all more or less centrally oriented. So yes, there is a dependency. They are all within that envelope there, but more. They are towards the middle. So can we say, oh, that's a normal then? We can't say. We can't go that far. We can't go, no, it's a normal. It may be symmetrical, yeah, and this triangular seems to be symmetrical. Why does that triangular seem to be symmetrical? Why does it seem to be the same for both sides? Yes? Yes, because you can see that that line is almost smack on in the middle between that all the time. It's a triangular that's going to be almost on the middle all the time. Yeah? So what has Neuendorf told us? If you were to sample that value, well, you work the minimum, you work the interpolation for the most likely, you work the interpolation for the maximum, you in Excel, you point those 3 cells to the spaces on risk variable. That would have taken weeks and months of statistical work, you know, by other sciences without the computer, years before. You know? Now it's doable within minutes. Okay, the last one. The triangle is skewed to a certain side, but we can also see it, can we? We can see that that triangle is towards the maximum. So it makes sense having plotted it like that. Yeah? So look at the difficulty of all of that, envelopes of probabilities, and we can do lines of example. I am enthused, to say the least. Okay, what about this? Let me just draw one for you. Let me just draw one for you. I'm going to draw it over there with these very good pens that I have. We want to look for one that... No. Yes. Yes, okay, that will do. All right. I'm going to grab something like that, okay? All right, so that's going to be like that. It's going to be like that. It's going to be like this, right? But I am going to do something like this. How does the triangular look for that one? Left? Is it skewed to the right? Well, we can see that the points are concentrated right there. What do we do? Can we say it's symmetrical in the middle? Can we say it's to the left? Can we say it's to the right? What can we say? We can say that over there, towards that area, it's going to be like that. Towards this side, it's going to be like that. And over here, it's going to be like that. So it's going to be a changing one. We don't care. It's triangular, and we know that every time something is called. If a value for random variable, I don't know, I'm going to do S and T here. S and T. If a value for random variable S is plotted to the right-hand side, it'll automatically go, you know, bang, bang, and bang, and stick the three values on the triangular cell that we have. But that will, without us even realizing, it'll be skewed to the right. Remember the language? When things appear skewed to the left, you say it's skewed to the right. It doesn't work with me, but that's the way that the jargon is. If something is sampled around here, well, bang, 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 your distribution for the next sampling becomes defined completely, automatically, but it's going to look like one that's skewed in the other direction. And if you sample something around the middle, bang, 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 the distribution is going to look pretty symmetrical. Okay? So this is the famous envelopes of probabilities. Interesting? Oh, very interesting. Okay. Oof. Remember when we did trees, we did one variable, and then we did two variables, because it's like the matrix, X and Y. And then we had a third branch on the tree, and that would complicate everything because it would become a cube. There you got it. That's your third variable in a row, depending on the previous two variables. It becomes a volume now. That's our curve that we had before, that will be sampled that way. We sample this way and probably got a result the other way. We won't go into that, but all I'm saying to you, we lose track, we lose the visibility of these things very damn quickly. Yeah? So what we do are simple mortals, simple practitioners. We just implement. We know that as long as we have the dependencies all right, you know, the sequences and the calculations, the results are going to be fine, but do not try to imagine it, what the solution looks like in a pictorial way, because you may end up in the sanatorium, you know, very, very quickly. Okay? So Neuendorf has done us all a favor, is allowed us to be able to do these things. Okay? So what are we going to do? We're going to have a linear, we're going to have a dependency for Monday. We are probably going to have a dependency with low, medium, and high. Am I going to throw curves? Am I going to ask you to linearize by segments on Monday? No. You're a little bit easier than that. It'll probably be something like this, you know, with a clear low, a minimum, and with a clear, you know, a minimum, most likely a maximum. It'll be something like that. There may be a couple of those. We may end up in the end interpolating. It'll be simple. We can't do something too deep on a section like that. Okay? So straight lines are easier to handle. So we've got to linearize everything. That is the trick when you have curves, linearizing by segments. So this is what we were doing before, right? I forgot that I had that there. It's shown very clearly, you know, that when the cloud of points suggests that that's format, well, you got triangulars, but they are skewed in opposite directions. Yeah? Okay. This is a bad graph, but if you had that sort of graph that I'm going to try not to give to you, you would have a little bit of a segments thing, yeah? Because the bottom of the cloud of points is really from this point on the left here to this point on the right. So for your range here of your bottom line, you would have segments. You would have that segment to there, a linear, the equation of a straight line, and that to there, an equation of a straight line, but different one. So your range will have to be defined using two straight lines. For the maximum, it will be the same thing. You know, you would have that segment there would have that straight line, and this segment here would have that straight line. So if the cloud was one that looks like that, you would have a little bit of segmentation there. Don't worry, we're not going to go that far either, but it's letting you know that can happen. Okay? I think we've got time to do a little something else. Okay? So this, what you've been seeing here today is chapter 7 and 8 of Neuendorf's, of the Bible. Yeah? We're going to do something very simple now, that it may just end up being an exercise in the exam. I don't know if it'll be. I will have to ask someone that knows. So if you don't believe me that it may be in the exam, just ask me, right? And we will see what happens, okay? Maybe I know something. So what are we going to do? What are we going to do? We got a little thing, area under the curve. When we don't have a computer, when we don't have anything else, where do I have it? Area under the normal curve. This is just so I can give you an easy exercise for the exam, all right? That's the only reason that this is here. So you should be appreciative of me keeping you for a little longer. Okay? This is the area under a curve. Okay? We use tables with published numbers, like we had to do at the start of our careers when we had paper tables to calculate logarithms. Have you ever seen them? You calculate your logarithm with calculators now, but we had to use paper tables, you know, and locate the right number. And I don't know how Gustav Eiffel built the Eiffel Tower. You know, what calculations he came up with at that time that he was able to do it so neatly. I mean, now we would have a bunch of engineers working for a couple of years to do one of those, but he did it, I've got no idea, just with pen and paper and with the abacus, right? Okay, this only works for normal curves, which are the ones shaped that way, nicely symmetrical, okay? The area under the standard normal curve that corresponds to the proportion that you see there is calculating something called the Z-score. Z doesn't stand for zombie or anything like that, you know, although there's a Z movie there by Brad Pitt or something or whatever it is. It's not that. The Z-score is determined as that equation that you have there. Z equals X minus the mean over the standard deviation, where that is a symbol for mean and the other one is for the standard deviation, and that I'm totally sure, although you keep obstinate silence about it that you all have seen and studied at some stage of your educational careers, and you're just keeping a low profile by not telling me, right? I am positive about that. So you use the Z table to work out the Z score. So far, so good. That corresponds to the Z score that corresponds to the shaded area. So obtain the normal value using that equation there. You know, if you want the x, you can just turn the equation around a little bit. We'll look at just a couple of examples. It's not some examples, just a couple of them. The oil price distribution that you see there has a mean of $50 and a standard deviation of $15. What is the probability of having a oil price $80 or higher? Simple. The Z table comes to our aid, right? Okay. We do some calculations first. We're going to find the Z score. The Z score was, as per that formula, equals to the x that we are interested on minus the mean, all of that divided by the standard deviation. The mean is 50, the deviation is 15, and x is 80, right? Because it's what we're trying to look for. Okay? So the Z score is 0.9772. We go to the score, right? Sorry, let me just go back. I forgot the number already. The Z score is 2.0. Okay? So we go to the Z table to find the 2.0. Where is it? These are the minuses, so that means that they are on the left side of the curve. The pluses shows the right side of the curve. So we look for the 2.0 here. It's not 2.1, it's not 2.03 or 2.05. It's luckily 2.0. So that is the one that we are looking for. This is 2.0 plus 0.00. So it's 0.9772, right? That's the area on the left of the point, right? If the score had been 2.07, the calculation, we would have done 2.0, travel to the right of here, and that's a 2.07. The area under the curve would have been 0.9808. But for this one, it's 0.9772. So it means that we are looking for what's above $80. We are looking for the area on the right-hand side of the number that we are looking for. So it's got to be the complement. It's only 2.28% chances of a price higher than $80, given the conditions of standard deviation and mean that we gave it, and knowing that it's a normal distribution. Okay? Another one. What's the price now? Okay? For what? What's a P90 price? What is a P90?